Welcome to 10mintuesCS. 1381 Design a stack with increment operation. In today's problem, we need to implement stack that supports increment operation on its elements. Usually, whenever we have a stack kind of data structure, we do not have access to the elements which are below the peak element. The peak element will be the element which is last added. So it follows last in first out LIFO principle. And we cannot make any operations in over these elements, but we can just pop or peek the last added element. So we need to implement these four functions. First is the custom stack, which we initialize with the maximum size, that the maximum number of elements in the stack that can be added. Then a push, where we add an integer x to the stack if our stack size hasn't reached maximum size. And in pop, we need to pop and return the top of the stack. If the stack is empty, we can return -1. And increment function, we need to increment the k element with the value val from the bottom. So let's see, this is our stack and we have few elements over here, and let's say k is equals to 2 and value is 3. So for all these two elements from the bottom of the stack, we need to increment their value by val, that is increment by 3. Now how can we implement this? We can clearly see that we should have access to the bottom as well as the top, right? And for that, because whenever we need to push something, we will push it from the top, and we need to pop something, then also we will use our top pointer. But if we have to increment something, we need to increment it from the bottom. So in this kind of scenario, now we need two pointers that should be pointing to our top, and the other one which will be pointing to our bottom. So in yesterday's problem, we saw that for such operations where we need to get access of the two extremes of a data structure, we can use a doubly linked list. Now here, initially we will have our head pointing to our tail and tail pointing to our head. Now whenever we want to push something, we will push it from the tail. So tail will have the latest elements. Let's say we had few more here. And whenever we want to pop something, then also we will pop it from the tail. So if we visualize it based on stack, so our tail will be pointing to the top and our head will be pointing to the bottom. And whenever we want to increment, we can use our head pointer. Now let's say we have to increment k elements. So we can create a current node which will be head.next. So it will start from this one until here, while our current is not equal to tail, that is we haven't reached the end of our data structure, and the number of elements that we need to traverse is greater than 0. For that, we can increment the value of our current node by the value itself. And while doing so, we should keep on moving our current to our next node. This way, we can implement all of these data structures optimally. First, we need to create a node class. We should have a value, previous and next, and while initializing the node, we can assign it the value and previous and next will be null in this case. And a custom stack will have a head, tail, max, which is the max size, and the current size of our custom stack to check if we have reached the maximum size or not. So initially our head and tail will be pointing to each other. That is, we have a empty stack and we should have our current size equal to 0 and maximum size will be equal to max size. To implement our push function, we can check if our current size is equal to max size, that is, we cannot add more elements. So we will just simply return, else we will create a new node and add it to our tail. So let's say we have our head and we have our tail. If it's the first push operation, we have both of them pointing to each other, and now we are creating our new node with the value x. So what will be our previous node? Previous node will be tails previous. So this is our previous node. It can be head or any other node. Now our new nodes previous will point to the previous node, and new nodes next will point to tail, and previous node next will be pointing to our new node, and tails previous will be pointing to our new node. Now we have added a new link, a new node here. While doing so, we are adding an additional node, so we should increment our current size. For pop, first we need to check if the data structure is empty. In that case, we should return -1. Now how will we check if it's empty? For that, we can either check that our current size equal to 0 or our tails previous and heads next is pointing to each other. If that is the case, then we can return true, else we can return false. Now once that is done, if our data structure is not empty, in that case we need to pop the elements. So we need to pop it from the tail. So let's say this is the pointers. Now we need to pop this element. How will we do that? This will be our delete node, that is tails previous, and we have our answer, that is the delete node's value which we will be returning, and our new previous will be delete nodes previous. So this is our new previous. Now new previous, delete nodes previous will become null, and delete nodes next will also become null. And now it is not pointing to anything, so this will be collected by our garbage collector and will be removed. Now we need to create pointers from our new previous to tail. So our new previous next will be pointing to tail, and tails previous should be pointing to our new previous. And finally, as we have popped a node, so we should decrement the size of our current size. For our increment function, we have to take all the elements from the bottom, that is from the head size. This is our bottom, and we have to run a for loop until the number of elements that we need to traverse is greater than 0, or our current, that is, let's say we will start our current from head next hasn't reached tail. So for all those elements, we have to increment its value to val, and each time we have to keep on incrementing our current pointer. Let's try to submit this code. It is the exact code that we wrote there. Yeah, it passed. Now let's look at the time and space complexity for it. For our increment function, as we are traversing over our data structure, our time complexity will be minimum of either the k value or the size of our data structure, that is the current size. And for our custom stack, we are just initializing the data structure. We do not have any for loops or any traversals. This will be O of 1. Similarly, our pop function, here also we are just removing a node without any traversal or anything. We are just updating the pointer, so this will also be big O of 1. And our isEmpty function is also checking just the variable value, so this will also be O of 1. And our push function is also adding a node and updating the pointers without any traversals. This is also O of 1. So overall, we were able to implement a custom stack in O of 1, push in O of 1, pop in O of 1, and increment with the minimum of k and our current size. The space complexity for this will be big O of max size, as it can go up to max size. Thank you for watching.